Hello everyone, I am Gopalakrishna Reddy Sanampudi. I am currently pursuing my master's in International Institute of Information Technology, Bangalore, which is located in India. Today I am going to present design and evaluation of M-term non-homogeneous hybrid Karatsuba polynomial multiplier. This is the agenda for today's presentation. Now let's start with the abstract. This paper mainly focuses on finite field multipliers, which are used in modern cryptography systems. Initially, it introduces the current state of art composite M-term Karatsuba-like multiplier, which is also known as CMKA, which combines a schoolbook multiplier with a Karatsuba multiplier. In the lower bound, we will use schoolbook multiplier. In the higher bounds, we will use Karatsuba multiplier. It also proposes a novel non-homogeneous hybrid Karatsuba multiplier, which is an improvement to the current state of art. The paper also introduces a novel MATLAB framework, which is used for generating optimized HDL code. The proposed design is implemented on Zinc ZCU104 and synthesized using Cadence 45 nanometer process node. The MNHKA outperforms current state-of-art designs in terms of area, delay, and ADP. The proposed design is implemented for 64-bit, 409-bit, 1350-bit, and 2500-bit, and it shows a maximum ADP improvement of 27% in case of FPGA and 45% in case of ASIC. Now let's jump into the background. Multiplying large numbers has always posed a significant computational challenge. Traditional or schoolbook multiplication algorithms is cumbersome when we are trying to multiply the large numbers. However, in 1962, Karatsuba proposed an algorithm which reduced the computational complexity. Now, let's see the comparison between schoolbook algorithm and Karatsuba algorithm. When we are trying to multiply two numbers x and y, initially we divide these two numbers into two halves. Since it is a two-term multiplication, we divided this x into x0 and x1. The schoolbook multiplication algorithm is similar to how we do multiplication in real life. We will multiply this x0 with y0, x0 with y1, x1 with y0, and x1 with y1. That is, I have written in the form of equation here. Whereas in this Karatsuba algorithm, Karatsuba slightly modified this equation such that it requires only 3 multiplications. You can see here, this is the first multiplication, this is the second multiplication, and this is the third multiplication. So by modifying the equation like this, we are able to save few multiplications. For an n-bit multiplications, we require only n power 1.58 single-digit multiplications, whereas schoolbook algorithm requires n square single-digit multiplications. Now let's try to understand the terminology. This slide is just to show the difference between number of bits and number of terms. When we are trying to multiply two 10-bit numbers with a two-term multiplier, it is a two-term multiplier. We will divide this 10-bit into two equal parts, which is of each of 5 bits. Then we will assign these 5 bits to x0 and assign these 5 bits to x1. Like this, we will continue with the algorithm. When we are trying to make it a 5-term multiplier, we will divide this 10 bits into 5 equal parts. Then it results in a 5 parts each of 2 bits. Like this, we will do and continue with the algorithm. Here are the equations for Karatsuba algorithm for different terms. Here I presented only 2-term, 3-term, and 4-term, and it can be any number of terms. These equations are for recursive product. As I discussed previously, 2-term Karatsuba multiplier requires only 3 multipliers, unlike 4 multipliers for schoolbook algorithm. These are the 3 multiplications required for Karatsuba, and after generating these products, these can be called as a recursive products or partial products. We will shift and add these partial products based on these equations to generate the final result. These are the equations for 3-term and 4-term multiplication algorithms. This table clearly showcases the number of submultipliers required for each m value. You can see here 2 term requires 3, 3 term requires 6. Like this, this table showcases number of submultipliers required. As I said previously, we have to shift and add the partial products. This structure helps us to shift and add these partial products. This is called overlap structure. Here K is the ratio of number of bits to number of terms. This is the structure for 3 term and this is the structure for a 4 term overlap module. And finally, this is the generalized structure for the n bit m term overlap module. To summarize the previous slides, these are the 3 steps involved in Karatsuba algorithm. Initially, we have to divide the given input operand into m terms. Here, I am showcasing 2 terms, so we divided into 2 equal parts. Then we have to compute the partial products. With the help of these equations, we will compute the partial products. Then we have to shift and add these partial products according to this structure. This is a recursive algorithm because when there is a large input operand size, we will divide that operand into small problems, means small sub-operands, and again apply the same algorithm until single bit operations comes. Let's see an example. Here you can see it is a 4-bit multiplications. So according to this step 1, we have to divide it into 2 equal parts. Here I divided into each operand into 2 equal parts. Then in the step 2, I started to compute the partial products. In this picture, I am computing P0. To compute P0, again I have to multiply this x0 and y0. To multiply this x0, y0 according to all this Karatsuba algorithm, again I have to go to the step 1, divide this operand into 2 equal parts and proceed with the algorithm. Again, in the step 2, I went to calculate P0 and this kind of breakdown happens until single bit operations comes. That is the reason why we call this algorithm as a recursive algorithm. Now let's see the current state of art multiplier, that is composite m-term Karatsuba multiplier. It is easy to understand this multiplier with an example. For that, let's see an example of 256 4-term Karatsuba multiplier. Since it is a 256 4-term, we have to divide this 256-bit input operand into 4 equal parts, that is each of 64-bit. Again, we have to divide this 64-bit into a 4 parts, since it is again goes to the 4-term multiplication algorithm. Later, this 16-bit also goes to a 4-bit multiplication. This is how normal Karatsuba works. But for the composite Karatsuba, we are going to add a schoolbook algorithm in the last. As we initially discussed, this Karatsuba algorithm is most suitable for long bit widths. But here 4 bits is a very small bit width and schoolbook algorithm is more efficient for this 4-bit multiplications. Since it requires for smaller bit widths, the complexity of XOR gates is higher than the AND gates. So it is good to go with the schoolbook algorithms for lower bits. Now let's see the proposed M-term non-homogeneous hybrid Karatsuba multiplier. It is an improvement to CMKA multiplier, which is current state of art. The approach of breaking down the operand size homogeneously along the stages may not result in optimal hardware characteristics for CMKA. We can further improve the characteristics by configuring the recursive stages to non-homogeneous M values like we did here. Here you can see the M values down the stages are not constant. M values down the stages are not constant. We started with 4, 2, 2, 4. This is a multiplier of 64-bit MNHKA for the sequence 4224. This slide showcases optimal implementation of MNHKA for 64-bit. It is for the sequence 4224. It takes two 64-bit inputs. Since it is a 4-term, we will divide this 64-bit into 4 equal parts, each of 16-bit. And 4-term multiplier will contain 9 sub-multipliers. Each sub-multiplier will take two 16-bit inputs. If we expand this P0, it will become like this. It will take two 16-bit inputs, and since it is a two-term multiplier, it will divide this 16-bit into two equal terms, that is of each 8-bit. Since it is a two-term, it will contain three submultipliers. If we expand this, it contains three submultipliers again. Since it is also a two-term multiplier, it will divide this 8-bit input into two equal parts, that is 4-bit 4-bit. At the final stage, we have a school book multiplier. Like this, we have the structure for optimal m-term non-homogeneous multiplier for 64-bit. This is the generalized structure for MNHKA. We can see at the final stage, there is a school book multiplier. It is taking two inputs, and we are going to divide each input into m segments, and each segment or each term will be of length m by n. These are the submultipliers in each stage. Now, let's see MATLAB automation framework. The right part of the flowchart contains the MATLAB algorithm. It will take two inputs. One is the non-homogeneous sequence and the input operand size. Based on the bit width and this non-homogeneous sequence, it will generate the .v file, which we can synthesize and get area, delay, and ADP results. And the left part is the important part of the framework. Initially, we will decide the operand size, and for that operand size, we will generate CMKA, composite M-term Karatsuba-like multiplier codes for m equal to 2 to 7. Then we will synthesize them to generate area, delay, and ADP results. From those results, we will get the optimal value of m, which has lowest ADP. Then we will start to explore the design space by generating different .v codes for different sequences. We will, from here, we will send different m sequences, then we will get .v code, and we will synthesize it like this. We will do for a few iterations to end up with an optimal MNHK multiplier. Now let's jump to the experimental results. As we discussed previously, we developed this MNHKA for 4 bit widths, that is 2500, 1350, 409, and 64 bit widths. These bar graphs showcases area, that is LUTs, delay, and ADP of FPGA, and this tabular column showcases ASIC results. These red graphs showcases the M-term Karatsuba, that is the normal Karatsuba without school book at the end. And this orange and yellow showcases the CMKA multiplier, that is Karatsuba with school book. And this blue color bars showcases the proposed M-term non-homogeneous hybrid Karatsuba multiplier for different corner cases. And this green bar showcases the best implementation for this 2500 bit. For 2500 bit, it turns out to be the best implementation of MNHK is 26777. This sequence contains more sevens. That is because the best possible implementation of CMK is 7-term. As we discussed previously, we are doing CMK multiplier initially because just to identify that that is the best, like this sequence contains more sevens. If we start searching from these sevens, there is high tendency that we will converge fastly. And similarly, this is the results for 1350 bit multiplier, and these are the results for 409 bit. It turns out to be the best sequence is 4736, and for 64 bit, the best sequence is 4224. Now let's jump into the conclusion of previous 4 slides. Considering ADP as a figure of merit, for 2500 bit MNHKA, it shows a best case ADP improvement of 23% for FPGA and 22% for ASIC. For 1350 bit MNHKA multiplier, it showcases best case ADP improvement of 27% and 45% for ASIC. For 409 bit MNHKA, it showcases the best case ADP improvement of 21% and best case ADP improvement of 15% for ASIC. Similarly, for 64-bit, it showcases best case ADP improvement of 12% for FPGA and 16% for ASIC. Just to remind, we have used Xilinx ZCU104 FPGA, and for ASIC, we have used 45 nanometers cadence process node. These are few references which helped us to complete this research work. If you have any queries, feel free to contact me through the email ID, or you can directly ping me on LinkedIn. And a big thanks to ISVLSI organizing team, and a special thanks to my beloved professor, Dr. Madhav, who supported me throughout this research work. And I would like to extend my thanks to my co-authors, Ravi Kiran and Vasanthi. Thank you.